Finally, in example 9 of module 7.1 class notes, we have one more word problem to do with compound interest. Let's take a read through the problem and see what we've got. Tabitha estimates that she will need $20,000 for her daughter's post-secondary education when she turns 18. That is one cheap college. Moving on, if Tabitha is able to save up to $8,500, how far in advance of her daughter's 18th birthday would she need to invest the money at 7.75% compounded semi-annually? A lot of information to parse through there, but I definitely hit on the word compounded. So I'm thinking my compound interest. And this is definitely one of the most interesting problems that we're going to work both mathematically. Logarithms come into play. That's always fun when logarithms come into play, but also interesting in the sense of it's the type of question that is most interesting to answer. If I want to earn so much money, how long is it going to take me to do that? It's one thing to do, as we've done in previous examples in this module's class notes, to say if I know everything about how many years I'm going to invest and how much I'm going to invest, and then how much will I have at the end of the investment. Sure, and that's a perfectly valid and fair question to ask and calculation to make. But it's perhaps more interesting a question like this, where we've got a goal that we're trying to meet. So how much money do we need to invest, or how long do we need to invest our money in order to reach our goal? That can be a more interesting question to answer, and a more profitable question to answer as well. Certainly a worthy question to answer. So let's parse through the information that we've got here. She estimates that she will need $20,000. So by the time she finishes her investment, she will need a total of $20,000. So sometime in the future, when her daughter turns 18, she'll need $20,000. So her future value, FV, is $20,000. If Tabitha is able to save up to $8,500, and so she's going to invest $8,500, as it says, she would need to invest that money at such and such an interest rate. $8,500 is the amount that she's investing. So her present value is $8,500. How far in advance of her daughter's 18th birthday would she need to invest that money at 7.75% compounded semi-annually? So we know our interest per year is 7.75%, and we know that that is compounded semi-annually, which you read in the textbook means twice per year. So the number of compoundings per year is 2. And we can use that to calculate our nominal interest rate, I. That's IY divided by CY. So twice a year, she will earn 0.03875 or 3.875% interest. Then from there, we've got the number of compoundings. So how many compoundings will that go through? Well, it depends on how long she has it invested, and we don't know that. But here's what we can say. The number N of compoundings will be the compoundings per year times the number of years. We know that we're compounding twice per year, but we don't know how many years. So let's say twice per year for T many years. And it's how many years do we have to keep the money invested? That's the question that we're trying to answer. So 2T will be the total number of compoundings, and we're going to try to solve for T, the amount of time that we need to invest the money. Plugging all this information into our compound interest formula gives future value 20,000 equals present value 8,500 plus times 1 plus 0.03875 for I raised to the N, which is 2T, power. We work through some operations here. Let's divide both sides by 8,500. to get approximately 2.352941. And then in the parentheses, that's 1.03875, raised to the 2t power. Now we're trying to get t by itself. T right now is stuck up in the exponent. What do we do now? As we saw in Module 6.2, to get the variable down out of the exponent, it's trapped right now in the exponent. To get it down, to free it up, we take a log on both sides. So let me apply a natural logarithm on both sides of the equation so that I can use my power rule for logarithms and bring that to, I'm sorry, not just the 2, but the 2t, bring that 2t down out of the power using my power rule for logarithms. And now the t's not in the power anymore, I can solve. I can divide both sides by both the 2 and the natural log of 1.03875 to isolate t to get t by itself. T is going to be the natural log of 2.352941 divided by 2 natural log of 1.03875. Ugly, yes, and not a good answer for an amount of time that we're looking for here. We'd rather be able to interpret our answer by plugging this into a calculator and getting a number that makes a little more sense. When I do that, plug this carefully into the calculator. Make sure that you do so that you can verify that you get the same answer I do. I get t is approximately 11.25. So that I can then interpret that answer as, remember, t was the number of years, and the question was, how far in advance of her daughter's 18th birthday would she need to invest the money? Tabitha would need to invest that $8,500 about 11.25 years prior to her daughter's 18th birthday. So not when her daughter's 11, no, she needs a little over 11 years for the money to grow. So you need to start at that 18th birthday and go back 11 and a quarter years, and that's when you have to invest the money. So when she's 7 3/4, yeah, 7 3/4 years old, that's when she's got a deadline of I need to invest the money by that time so that I can have enough time to turn that $8,500 into $20,000.